So it's systems of linear equations in 3 variables. That means we no longer just work with x and y. We have x, y, and z. Okay, so our objectives are to learn basic concepts in systems in 3 variables, solve the 3 variables using elimination and substitution, and identify systems with no solutions, okay? And then solve systems with infinitely many solutions. So for example here, this is a basic solving, right? If you saw this, 4x equals 24 plus 6x, could you confidently solve this? Or go through the steps to do that? Yes, right? You would go through, you end up with x equals, so I combine 10x, and I try to go through and check it. And what ends up happening when I check myself, like, oh no, you did something wrong, right? That's the beauty of an equation. You can always check yourself. Okay, I know it sounds like extra work and it can be annoying, but check yourself is important. All right, so how does systems of 3 variable work? This right here is that I have 3 unknowns, and I now have 3 possible guesses for these 3 unknowns. In order to check that they're the correct unknowns without doing anything else other than guessing and checking, all I'm simply doing is plugging in and checking if they make true statements. Does that make sense? If they make true statements, then I know that it's correct. The key thing is when it's a system, it has to make a true statement for all 3 equations. Does that make sense? So when I test it out, I have -1, 2, and 2, and I'm going to plug it in. So for the first test, I have -1 plus 2 minus 2 times 2, and I want to know if it equals -3. So I'm going to go through, do the math. -1 plus 2 is 1. 1 minus 4 is -3. So it works for the first one, right? So I'm going to do it for the next one. So we have 2 times -1 minus 2 minus 3 times 2. 2 times -1 is? -2 minus 2 is? -2 minus 2 is -4, right? And then -4 minus 6 is? Negative what? 10. Does that equal -9? No. So this is not a true statement. So that lets me know that this is not the solution to this system. Does that make sense? Okay. Just because it's true for one, it has to be true for all in order to be the solution to the system. So I'm going to switch, and now I'm going to test out 1, 2, 3. So we have 1 plus 2 minus 2 times 3. Does that equal -3? What's 1 plus 2? What's 3 minus 6? -3. That adds up. So now we're going to do the next one. 2 times 1 minus 2 minus 3 times 3. Does that equal -9? What's 2 minus 2 times 1? 2. What's 2 minus 2? 0. What is -3 times 3? Oh, look at that. Checking the last one. We have -1 plus 2 plus 4 times 3. Does that equal 13? -1 plus 2 is? -1 plus 2 is +1. Plus 12 is 13. So our solution is 1, 2, 3. And it's the solution because it worked for all 3 equations. Yes? All right. Exactly. That's why when I stopped at the red, right? Because I knew it didn't work. So there was no point in me going on anymore. Okay. All right. So again, we're just checking and plugging, and that lets us know that we were correct. Yes? All right. Next, we're going to talk about substitution. So solving with substitution, you want to make sure your equations are written in standard form. So in standard form, that is your AX plus BY plus CZ equals your constant, okay? You're going to choose the equation that would be easiest to get a variable alone. So you're looking for when there is a coefficient of 1. And you're going to get that variable alone. Then you're going to substitute that in to 2 of the equations. Now that you're down to 2 variable systems, you then are going to eliminate by whatever method you choose, whether it's elimination or substitution. And then you're going to do some more substitution, find the 2 variables, and then you can always check yourself. The other method is elimination. Elimination works whether your leading coefficient is 1 or not. But the main thing here is you want to make sure that you have opposite signs, okay? So when you're choosing which one to eliminate, you want to make sure that the signs are opposite. You need to have a positive and a negative of the coefficient, otherwise they will not eliminate, okay? All right, so we're gonna start off here. Yes. Did you already go next? Yeah. All right, so this is an example of why elimination may be the easiest. The reason being is that if you look right here, I have all these x's, I'll have 3 x's. And there's one x that's negative, and then the other 2 are positive. So I can set up 2 equations and eliminate my x's and only work with my y and my z, okay? So that's what we're gonna do. We're gonna set up the elimination. So I'm gonna do equation 1 and equation 2 first. So I have x plus y minus 2z equals 3. Then I have negative x minus y plus 3z equals negative 1. When I combine, not only do my x's eliminate, but also what eliminated? The y's. So I'm left with 1z equals 2. Okay. Now I'm going to use the other 2 equations. So first I used 1 and 2. Now I'm going to use 2 and 3. So that gives me negative x minus y plus 3z equals negative 1. I get x plus 2y plus z equals 12. Again, my x's eliminate. I'm left with 1y plus 4z equals 11. Because I know the value of z, I can easily solve for y. So I'm going to take this and substitute into here. So we know y plus 4 times 2 equals 11. So therefore y equals what? 3. Okay. Now the last thing we do is go back to the original and you're going to solve for x. It doesn't matter which one of the equations you're going to use. I'm going to use equation number 1 to get x by itself. So I know x equals 3 minus y plus 2z. And because I know the value of y and z, can I solve for x? Well, yes, I can. So because I know the values of y and z, I know x equals 3 minus 3 plus 2 times 2. Z? Oh, I chose equation 1. So I chose equation 1 to get x by itself. And then I substituted in y and z. Because we know y is 3 and we know z is 2. Are we good? I used this one. And got x by itself.
Oh, okay. So that was time to see what the start of it.
Yeah, I used this one and got x by itself. And then I substituted in what I knew. So now we know that x equals 4. Because 3 minus 3 is 0 and 2 times 2 is 4. So my solution set is 4, 3, 2. Again, I chose elimination because I had an easy setup with opposite coefficients and I knew I could eliminate my x's and work with just 2 variables. Okay. All right. We're going to look at a word problem. So 1,000 tickets were sold for a total of 15,500. The prices of the tickets were $10 for children, $15 for students, and $20 for adults. There are 200 more student tickets than adult tickets. Find the number of each type of ticket sold. Okay, so we got to create our system ourselves. So we have 3 different tickets. We have children, students, and adults. Correct? We know that children plus students plus adults equaled 1,000 tickets because it said there was 1,000 tickets sold. Next, it tells us the cost. So $10 for children plus $15 for students plus $20 for adults equal 15,500. We need to do whatever fundraiser they did. To sell 15,000, make $15,500. Then it says there were 200 more student tickets sold than adult tickets. So we know that student tickets equals adult tickets plus 200. How do we feel? From reading and setting up. So that's your system. This one is leading us to substitution. The reason why my braces are horrible, I know. The reason why it's leading us to substitution is because it tells me S equals this. Do we see that? So we're going to use substitution instead of elimination. So everywhere there's an S, I'm going to plug in A plus 200. So for the first one, we have C plus A plus 200 plus A equals 1,000. I clean this up and I get, I'm going to combine like terms, which means I'm going to move my constant and combine my variables. So I have C plus 2A equals 800. Okay, I'm now going to do the same thing in the second equation. I'm going to substitute in for S. So when I substitute in for S, I have 10C plus 15 times A plus 200 plus 20A equals 15,500. That gives me 10C plus 15A plus 3,000 plus 20A equals 15,500. Again, you're going to combine, so like terms with like terms and move your constant. Yes. Yes, we're not there yet, but yes. So when I combine, when I write it's combined here, that gives us 10C plus 35A equals, got a 5 in there. What's 1550 minus 300? 1250? 3,000? 1250? 12,500. Tell me where. And I subtracted 3,000. 12,500, right? Sorry, I kept saying 1550. Because that's how I wrote it. I wrote a 5. It's 15,500. All right, so now this is your system to find your C and your A. Because once I find A, I then can find S. So this goes back to our 6.1 and 6.2, or our 6.1, where you only had to solve for 2 variables. And the method you choose to solve for 2 variables is totally up to you. You can do elimination, you can do substitution. What do you want to do? Want to do substitution? That's cool with me. So for substitution, I'm going to get C by itself. If I get C by itself, what does that look like? C equals what? 800 minus 2A. So now I'm going to substitute in. So I get 10 times 800 minus 2A plus 35A. I'm going to clean this up. That gives me 8,000 minus 20A plus 35A. Clean it up again. I get 8,000 plus 15A equals 12,500. So how would I solve for A? There we go. So we're going to subtract 800 and divide by 8,000, sorry. Thank you. And divide by 15. Minus 800. 8,000, Shauna. What's your brain doing? Divided by 15, and we get 300. So we know that A equals 300. So we know that there was 300 adult tickets sold. Now that I know how many adult tickets are sold, I can work backwards and solve. So now I know A, so I can find C. I know A, so I can find S. Does that make sense? So once I have that one variable, I can now use it to solve everything else. So I'm going to pull up my calculator. I mean, we could do it out loud. We're smart. So for C, what's 800 minus 2 times 300? 200. So we know that C equals, so children tickets equals 200 sold. Does that make sense? Then here, what is 300 plus 200? 500. So student tickets equals 500 sold. And then how many adult tickets were sold? 300. So adult tickets equals 300 sold. So we now found out how many of each ticket was sold based on the cost and the amount of money we made. Believe it or not, I mean, a lot of programs are like people who use programs to generate this information, but this is literally how moviegoers, when they're trying to figure out who came to the tickets or how many tickets they sold, when the tickets sold, we made this amount of a profit. This is actually a real example of where a 3-variable system could be utilized. All right, questions, comments, concerns? A lot of times with the word problem, the hardest part is just the setup. So make sure you're reading and using that math sense, that common sense to navigate your way through it. If you look through it, you'll see that whole answer. So as you go here, put it somewhere. Oh, I did. I thought I'd given myself a bigger room and I couldn't remember if I did or not. I did. Okay, so what I'm going to do is we're going to set up one and then I'm going to pause and let's see how you do by solving it. So if you have your scratch paper, your whiteboard, whatever you're going to use to try and solve it, we're going to set it up together and then.
I was.
All right, so here we go. 3 students buy lunch in the cafeteria. 1 student buys 1 sandwich, 2 sodas, and 2 candy bars, and it's $9. Okay, so we have sandwiches, sodas, and candy bars. So we're gonna let that be X, Y, and Z. So the first student bought 1 sandwich, 2 sodas, and 3 candy bars, and they spent $9. Another student buys 2 sandwiches, so 2X, 1 soda, 1 Y, and 1 candy bar, 1 Z for $9. So now we have 2X plus 1 Y plus 1 Z equals $9. The third student buys a soda, which is our Y, and a candy bar, which is our Z. They bought no sandwich, right? So 0 sandwiches plus 1 soda plus 1 candy bar equaled $4. What you guys are calculating is what was the cost of a sandwich, a soda, and a candy bar. All right. Is 5 to 6 minutes fair for y'all to practice? My hint to you is go with what's the easiest to eliminate or substitute. All right. And I'm gonna pause. All right, so let's go over this. It was brought to my attention that I wrote 3Z instead of 2Z, so that was corrected. So let's solve it. So the best thing here to think about is what can I eliminate? How can I eliminate moving forward? So if I decide to eliminate the Y's, I'm going to focus on my Y's or focus on my ones. It doesn't really matter, but I'm going to focus on eliminating the Y's. So you have equation 1, equation 2, equation 3. So the first thing I'm going to do is work with equation 1 and equation 2. To equation 2, I'm going to have to multiply everything times -2. So I'm going to multiply everything in equation number 2 so that this can become a -2y. I'm not changing anything about 1 because it's good to go. So we have 1x plus 2y plus 2z equals 9. Then I'm going to multiply everything in this row by -2. So that gives me -4x minus 2y minus 2z equals -18. When I combine, my y's cancel and my z's, so I'm left with -3x equals -9. So now I know the value of x. So x equals 3. Okay, so now I know the value of x. I can then either continue to eliminate or now I can plug in for x and solve just y and z. I'm going to keep eliminating and seeing and finding z that way. So I'm going to now use equations 2 and equation 3. So using equation 2 and 3, it's already a 1. I just need to make one of them a negative. So I'm going to multiply by -1. I'm going to leave the first equation alone. So my first equation I have is 2x. So I have 2x plus 1y plus 1z equals 9. My second equation, I have 0x minus 1y minus 1z. Is it a 1 and a 1? That wasn't very smart on my end. Just now paying attention to what I just did. Equals -9. And it's not going to help me solve anything because it's all going to eliminate here in a minute. Let's not do that. Erase, erase. Reverse, reverse. We're going to go ahead and plug in the fact that we know everything is x. Just pretend you heard nothing I just said. So we're going to plug in the values of x into the first two equations and just solve from there. So for here, we know that x is, my buddy, 3. So we have 3. So 1 times 3 plus 2y plus 2z equals 9. Then the next one, we have 2 times 3 plus 1y plus 1z also equals 9. So when I clean this up, I have 1 times 3 is 3. I'm going to subtract that to the other side. I have 2 times 3 is 6. So I'm going to subtract that to the other side. So now I'm working with 2y minus 2z equals 6. And then we have 1y plus 1z equals 3. So this could be an easy substitution problem. I can get y by itself and plug in for z. Which way you choose to go through and solve it is ultimately going to be up to you. Come on in. Or I can do substitution, elimination, and multiply everything down here by -2, which probably is the best thing to do. So if I multiply this whole bottom equation by -2, I'm going to end up with -2y minus 2z equals -6. That ain't bad math. Guys, why is this? What am I doing wrong? -4z equals. I have that z is 0. And I don't think candy is free. Pause. So in conclusion, your teacher did not choose great numbers for this system, and it's an example of a no solution example. So what this tells us about this student is that maybe someone got a discount, that maybe someone didn't pay the exact same amount each time, because there's no solution. And I even checked it graphically. So there's no solution. No solution. You cannot estimate what each one paid because if for whatever reason someone paid less or a different amount. Did y'all come to that conclusion too?
Yes.
Yeah. Okay. All right. Well, that concludes 6.3.